Today what I'm going to do is keep going on. I'm going to keep going on the antennas. I'm going to tell you right now for the fiber optic section, optical waveguides, I'm not going to test you directly on that. If I'm going to do anything, it'll be later in the chapters, much later, what it has to do with in the microwave section. I'm not going to test you on that per se because, frankly, a lot of stuff it's a very small amount of theory for when you finally derive the equations. You're more like a technician just using equations at that point. But today, what I do want to do is get into the next chapter, and this is antennas. And talk a bit about antennas. The way Dr. Wentworth's book does it, he starts with the assumption we can find the gain of an antenna, or the directivity. Then he goes backwards and starts identifying how you get that from an actual antenna. And then he goes through a wire antenna and develops equations for the electric field from a wire antenna based on first principles. He works backwards in this one, but it's with a purpose, because the most common thing you see when you deal with antennas, and you buy one, is something called the gain of the antenna. So with that in mind, this is going to be antennas. And what we're going to start with is the concept of gain, directivity, and it's really, I'll call it antenna impedance. And I'm going to make all this clear. I just want to tell you what we're thinking about. So when you go buy an antenna, it has something called the gain. It's usually the maximum gain on it. And then it has something where it tells you how that gain's distributed. And it gives you a polar view, a polar pattern of where the maximum power density is and the minimum power density. These are called lobes of the antenna. Just keep this in mind so when we're going through this, you'll understand what I'm up to and why. But before anything, you have to understand something. For an antenna to operate as an antenna, you have to be so far away. It's called in the far field. Now, I do this. Did you have me for Emag2? Anybody? All right, if you have me for Emag2, you know this, but oh, I'm so sorry. Yell at me if I don't ever do that. Thanks again. What happens is this. You have to identify how far away you have to be from the antenna before the actual wave is basically just a propagating wave. There's no electrostatic or magnetostatic energy. I do this. I say if you have a capacitor, just a capacitor, and you charge those plates, you get a voltage. If you move a meter away from that capacitor, you would be able to measure, at least theoretically, the field, the electric field, right? That electric field is stationary, it's not propagating. As a matter of fact, you can get all the energy in the electric field from that capacitor out of it if you just put a resistor across it. It would short through there, and all the energy in the field would then be discharged through the resistor and would dissipate as power. Follow me? Now that field's not propagating. If you have an inductor, just an inductor, and you put a DC current through there, a magnetic field exists, and you could measure that magnetic field. Not a mile away, but nearby, there's a magnetic field. That magnetic field is not propagating. The magnetic field and the electrostatic field I'm talking about have a the minimal rate that they change is 1 over r squared. Follow me on this? Now, propagating electromagnetic energy, it's really can be said as the ensemble of a whole bunch of photons. If you know something about electromagnetics, you know that the electric field of light and everything else is composed of photons if it's propagating. If it's not propagating, they're called virtual photons. And I'm not an expert on this, so don't ask me questions. I'm not a quantum physicist either. But anyway, what you have to understand is when we talk about propagation, we're talking about real photons being launched forever. Most of the time we don't talk about photons, we talk about electric field values in here, unless we're at extremely high frequencies, like optical frequencies. So how far away do you have to be from an antenna before you can forget about the near field, electrostatic and magnetostatic energy associated with that antenna? And something else I didn't say, but all antennas, regardless of how they're built, inherently have some electrostatic energy around them and some magnetostatic. Do you follow me on this? But that energy is never launched. The stuff that is launched is the propagating field, and this tells you how far you have to be from an antenna before it is in fact propagating. This is an equation. Well, I'm going to just show this to you. This is the most common form of this. It says you have to be for the far field propagation. They use a distance r. That's from the antenna in any direction. And it has to be greater than 2 times something called it's really d squared over lambda. Now lambda is just free space lambda, it's c over f. You can call it lambda naught. But d is, it's the maximum dimension of the antenna. And I'm going to tell you one other thing. This is for what are called aperture antennas. They're not for just thin wire antennas. And what the maximum, this D value would be, for instance, if you had something that had an antenna, say it was a horn antenna, and you're looking down the cross section of the horn antenna. You know what I'm talking about when I talk about a parabolic antenna? It's just a dish, right? When you're looking straight at the dish, you have a diameter. That would be the maximum dimension. If you have something like this, it's a horn antenna, then you're going to have some, let's call it W, and some height, H. Well, the maximum dimension is this, which would be the square root of H squared plus W squared. Follow me on this? So it's always the maximum dimension of the cross-sectional area of the antenna. So with horn antennas, with dish antennas, with any type of an elliptical radiator, you always look at that dimension. Now, if you look at this equation, one thing that jumps off the page at you is the smaller that wavelength, the further I have to be. Got it? The smaller the wavelength, the further you have to be. As an example, I just want to make sure you get a feel for this. Suppose I have an antenna that's going to be 3 meters, a horn antenna, by 3 meters, right? And I want to know how far away I have to be from this before I can just assume I'm in the far field, it's a propagating field. Follow me on this, guys? Well, now you would go right here, and you would find that dimension would be 3 squared plus 3 squared square root, or it's really square root of 2 times 3, right? So this is square root of 2 times 3 here. And that means to be in the far field, I have to be at least, and let me give you a frequency. Suppose I'm operating at 300 megahertz. Anybody know why I chose 300 megahertz?
Cancels with.
Because it's going to make the wavelength 1 meter. And lambda is C over F, means it's 1 meter, and I like that number. I can deal with that one. So this has to be greater than 2 times, then it's going to be D squared. Well, when I squared this dimension D here, does everybody see that's D right there? Let me put it down, but that is the maximum dimension, right? Cross-sectional dimension. Follow me? When I square that, I get what? 2 times 9 over 1. So it's really 4 times 9 or 36 meters. Okay? I do this because sometimes you're out in the field, and if they don't underscore this fact, you don't know how to calculate that. I mean in the near field or far field. It's a little different, by the way, for thin wire antennas, but that comes a little later. So what would it be? That's at 300, at F equals 300 megahertz, right? Well, what happens if F is equal to 3 gigahertz, 3 times 10 to the 9th hertz? Well, then I have to be at R greater than 360 meters, big difference. Follow me? Everybody see that? You have to be further and further away before you can assume far field effects. And we'll get this from the equations later, and it's just something to be aware of. You don't realize how sensitive that is. But you go from 300 megahertz to 3 gigahertz, an order of magnitude, and all of a sudden I have to be an order of magnitude further away, basically, which is important to understand. Follow me, guys? All right. So we're in the far field. Now, when we talk about antenna, scam likely. It's probably somebody in this class. I don't know why this does this to me. I need a new phone. This thing's been through the war. All right, back to this. Dr. Wentworth's book talks about this, but I don't even think he gives an example of this, and it's important. And some people say, well, why do you care about this? And here's one reason. If you're real close to an antenna and you're trying to do anything like impedance match, estimate signal strength, if you assume only far field effects, you're gonna be way off, way off. You wanna be in the far field when you assume anything about propagating field equation. Some of this stuff will be more apparent when we talk about microwave dish and something called a Friese transmission equation. It's why we need to know that information. Or it'll be more obvious why it's important. Next thing we're going to talk about, and we're going to go through gain and directivity without actually going through the development of the power density from just a thin wire antenna. So the first thing I talked about last time, I said, if you had an isotropic radiator, you have an antenna here, and it has a transmitted power T, PT in watts, say 500 watts, something like this. If I come a distance R away, and if this is an isotropic radiator, then the power density here, the average power density, would not be a function of any angle. It would just be a function of distance away. And the way you get it is just take the total power radiated over the surface area of a sphere. And that would be actually the average power density from an isotropic radiator. Can anybody give me an example of an approximate isotropic radiator? I know you know it, from anything. Anything. It doesn't have to be an antenna, man-made source. How about the sun? If you come out from the sun a given distance, right? The intensity, radiation intensity, is the same regardless of what azimuth and what elevation you're at. Do y'all agree with that? As a matter of fact, a light bulb, to a large extent, could be thought of that too. Now, both of those I'm using only to give you an idea of what I mean by an isotropic radiator. It radiates the same in all directions. Now, antennas don't do that, but here's the way gain is used. We start by taking this equation. That's an isotropic radiator. Gain tells us how much better it is in a certain direction. And gain is a function of theta and phi. So as theta and phi change, the gain will change. Usually they talk about max gain of an antenna. They give that to you if you buy an antenna. And they also they'll talk about the actual beam width. And the beam width is how wide the first lobe is. This comes a little later. It's beam width in an antenna. The higher the gain, the narrower the beam width of the main beam. Follow me? It's one of those things that happens. Yes?
That coefficient on the top, P average equals something times the G, replace that?
This is transmitted power.
Okay.
This is, why don't I do an example? This is R is just in meters squared, how far away you are. And G is gain, it's unitless. It tells you how much better it is. I'll give you a simple example so it'll drive this home. Here's a real example. Say I buy an antenna that has 20 dB worth of gain in the main lobe. That means it has a factor of 100 of actual gain. So I've got 20 dB, and this is an example. So gain is 20 dB, or in a linear sense, it's got a value of 100. And everybody knows when we talk about gain in dB, well, maybe you don't, that's going to be equal to 10 times the log of the actual linear gain. So if you got 100 there, 100 is 10 squared, right? The log of that is 2. 2 times 10 is 20. 20 dB is 100 linear gain. Follow me, everyone? Now that's max. So just say this is max gain. I bought an antenna that had that. I'm aiming the antenna in the direction of the maximum. So now I say, here's my antenna. Right? And I'm going to be at a distance of, say, 2,000 meters. So I'm 2,000 meters away. And I'm going to transmit a power of 5 kilowatts. Continuous power, 5 kilowatts average. Follow me? So I want to know at 2,000 meters what the actual power density is. So I want to know what the power density is. And I want to know what the electric field strength is. I'll call it E, the electric field strength there. This is a reasonable question that you should be able to do after this lecture. Can everybody see this? Everybody comprehend what I'm saying? So for starters, I want to find the average power density here, right? How do I do that? Well, P-Av would be equal to the transmitted power, right, using that equation. Transmitted power, which is 5,000, right? Then I divide it by 4 pi. R is 2,000, so 2,000 right here. I square that. And then I multiply this whole thing by the gain. That's going to give me a number, isn't it, class? What do you get for that? Well, that's 5 times 10 to the third times 10 squared is going to be 5 times 10 to the fifth, right? Then I have 4 pi, and that's 2 times 10 to the third squared is 4 times 10 to the sixth. And you can give me that. Let's see, what do we got here? This is going to be 10 to the minus 1, right? And then I have 16, I'm going to have 5 over 16 pi, and that would be watts per meter squared here. So that is going to be the power density at that range. Do you follow me? Now remember, that's power density. It's max power density, right? That's at that range. So what's the electric field? Do you remember from propagating waves how to get the electric field from the power density? If you're in, let's assume this is air too. This is air. Anyone? Good.
V squared over R.
Yeah, you know that if it's lossless, if it's air especially, we know that the average power density is equal to 1/2 magnitude of the E field squared. That's the magnitude of the E field, by the way, divided by eta naught. It's not the RMS value, it's the average value, or peak value, pardon me. So here, what do I get? Well, that's 5/16, or 16 pi, so I'd have E itself, magnitude of E, would be equal to 2 times eta naught's 120 pi, times that, which is 5 over 16 pi, and then I would take the square root of that. Wouldn't that, class? Yes?
Is it supposed to be 0.5?
Pardon?
You left off 10 to the negative 1 on the power average.
Ah, you're right. Thank you. So it's
69.
0.5. Thank you very much. 0.5. My bad. You're absolutely right. What do you get when you do this?
24 over 16 over 2.
Do the square root,
over
please.
16.
All right, all right.
Root 3/4.
I'm not sure yet. Go ahead. You might be there. You'd be great on Jeopardy. 120 pi over 10 pi is 12 pi over pi is 12 times 2 is 24 times 1/2 is 12, square root of 12, square root of, so you could say square root of 3 times 2, right?
1.74.
What did you get? And times square root? 2.74? 2.74. Is that right? Okay, thank you. 2.74 volts per meter would be the electric field. Out of curiosity, how would I get the magnetic field? Say again? That's right. Well, divided by 8 or not. Yeah. Divided by 8 or not. All right. So you could get the magnetic field. Everybody follow me on this, class? This is a simple example that hopefully helps you understand this. That's the reason I did this. You see how gain is used to calculate the power density at a given range. And that's what it's really useful for. Now, after that example, we get back to what I was up to. And you know, when you buy antennas, any type of antenna, it's always in dB the gain. It'll be dB iso usually. It means compared to an isotropic radiator, but it's always going to be in dB. And one other thing I'll tell you with antennas, there's 2 things you always look for. This is just the technical bit. You always want to take a look at the max gain. You always want to take a look at how far down the side lobes are. If they say 20, 30 dB in side lobe, that means it's 20 or 30 dB less power in the side lobe than it is from the main beam. This is important. Then you look for the impedance, the driving point impedance, because you have to know that in order to do any kind of design. You have to impedance match these things. Those are the 3 things you really look at. There'll be also things like maximum power that they can handle. You have to be aware of. If you're talking about like a radar, you can't overpower an antenna, you melt the thing. You got to be careful about stuff like that. Now, so where did this gain come from? This is where we're going. So first, let me say that gain in general, the term gain, is really in itself composed of 2 things. It's composed of something called the antenna efficiency that I'll explain in a second. That's EF. Antenna efficiency. And it's times D, and D is called the directivity. Now, in the real world, people use directivity and gain interchangeably because the efficiency of any antenna that's really used for commercial things is very high. It's like 99% or 0.99. It's just about 1, you follow me? So when they say gain or directivity, they're talking about the same beast. But really, and this is for some cases where all of a sudden you have an extreme bandwidth or something and certain frequencies, you all of a sudden, now you're gonna have lower efficiency. It might go down to like 0.9. Then you have to be careful with gain and directivity. The directivity D right here is something that's calculated mathematically, and this is what we use for the calculations once we have the power density from a thin wire antenna. That's where we're going. So what is directivity? Well, really, the directivity, as Dr. Wentworth puts it in his book, is equal to the normalized power density, and I'll get to this in a second. That's a function of angle, both theta and phi, over the normalized power density's average value. Now I've got to tell you about how you do this. Because he starts and he throws this out there, but this thing you don't know what it is yet. So what is the normalized power density? Take note of this. In general, when you have a power density, PF, right, you're going to have something that's going to be a function of both R, theta, and phi. Agreed? Here's what you do with this character right here in order to do this right. I'm not going to go into all the details. I'll tell you how you work with it. You just set R equal to 1 meter and forget about it. It works for every value. It's going to work for 1. Even if we're in the near field. Don't worry. It won't matter. Because this is a fictitious value. Cancels out anyway. So let it equal to 1. Then when you have this, all right, this is the, by the way, when I put PF here, this is the power that's actually, the power density out there, all right? This is almost one of those things. I'm gonna get in trouble. I'm gonna use this symbol right here, P, just P for the transmitted power, and this is in watts per meter squared. So now, if we take P right here and divide it by the maximum value of P, we're gonna get something called the normalized value. It's still a function of theta and phi, but not R, because I set R equal to 1. Are you with me on this? Now when you do that, this is a normalized power density. For instance, if you want to, for instance, what I'm talking about. Suppose I said the transmitted power was 100 over R squared, all right? And it's going to be times the sine squared of theta, KR. I'm going to say that's the power density in watts per meter squared. Follow me? Now if I have that, what would the normalized value be? Well, I told you set R equal to 1, right? To get rid of it, basically. Now when you do that, well, what's the maximum possible value of that function? Isn't it 100? Because sine can only have a value of 100, right? You all see that? So that means the normalized power from here, P normalized as a function of theta and phi, theta only in this case, would just be equal to the sine squared of theta. Everybody see that? The normalized power density will have a maximum value of 1, all right? And you took the power density and you divided by the maximum possible to get that. Now it's going to go to 0 at points too, isn't it? Whenever the sine is 0, it's 0, right? But that doesn't matter. Yes?
What's inside your parentheses?
This theta and phi, it's the arguments. It's just P is a function of theta and phi, but really not phi, it's not there, even though it could be there. But it's not a function of R, that's my point. Now you come down here, you have this, but that still doesn't give you directivity. Now, this is important, you pay attention to this. Now you have to find the average of the normalized power density. Please listen carefully to this. This is where people mess up. So how do we find the actual average value? And I'll put it right here. P av, or P normal av, which I don't like doing it this way, but Dr. Wentworth wrote the book, not me. So what we end up doing is we have to integrate the normalized power density. So that's the thing up here. And I have to integrate it over a surface of a sphere. Over the surface of a sphere of where R is 1. Got it? So if it's 1, you don't worry about it. It would be normally R squared times sine theta, but this is times sine theta d phi. So theta goes from 0 to pi, and phi goes from 0 to 2 pi. And that is not quite the average power density. That is the total amount of power radiating averaged. I mean, when I divide by the maximum value. But then you divide it over the surface area of a sphere of r equal 1 or 4 pi. Really, the surface area of a sphere, if you think about it, of r equal 1 would be what? Well, the area would be equal to a double integral of r equals 1, so it's r squared. This is going to be what? Times sine theta, right? And then it's going to be d theta d phi from 0 to pi, 0 to 2 pi. When we integrate phi from 0 to 2 pi, we get 2 pi. Integrate sine theta, you get minus cosine theta. Evaluated from 0 to pi, you get a 2. You get 2. 2 times 2 pi is 4 pi. This is just 4 pi. That's the area. So this is the average value. Are you with me? Now you'll notice P normalized is in there, and it's multiplied by sine theta times d theta d phi. Does anybody know what this is called? There's a term for sine theta d theta d phi in the math. If you took some advanced mathematics, you've probably seen it. That's called a solid angle, because now we're not in just degrees or radians. We're in degrees radian, or really radians squared. It's called a solid angle. It's in steradians is the terminology. This is usually given the symbol d capital omega. And that is in steradians. That's what it's called. Now that term I don't worry about. I want to make sure at least you keep hearing it from me. So if somebody brings it up in a lecture somewhere, or you're reading a manual, you'll understand. Steradians is the solid angle. All right, it gets rid of r. There is no r in this. When you talk about steradians, think about this. If I'm looking out and I say if I go from here to here, I got a 70-degree spread, right? Well, with steradians, that's one dimension. With steradians, I see a cone, all right, for instance. And I say within that cone, I have maybe 0.8 pi steradians. The whole entirety of my view would be 4 pi steradians. Follow me on this? But the cone just has a portion of that. So oftentimes with radar and things like this, they say, how big of a, as far as the main beam, how many steradians are in there? That gives them a real good idea of how actually focused it is. If you got almost nothing, it's like a pencil. It's called a pencil beam antenna, like a laser just about. And there you can get something close to that, but you can never get everything directed in one direction. You can't get a pure pencil beam with anything but a laser. So that's just the omega, but you don't need to worry about that. Anyway, now getting back to the equation here. Now that I've introduced normalized power density, the average of the normalized power, and the concept of directivity here, what that means is the directivity is actually equal to the normalized power density of theta and phi over the normalized average power density, which means it's that right there. So the 4 pi comes upstairs, and then downstairs I get this double integral of the p normalized of theta phi times the sine of theta d phi. And here I go from 0 to pi and 0 to 2 pi. And that's the equation. And you'll notice for gain, or for directivity right here, what you're actually getting is directivity is a function of theta and phi, right? Now, I'm trying to do this in a way that's, at least to me, the most logical, to try to explain these concepts. This is getting more and more into the mathematical definition of how you calculate gain, if you knew what the average power density is. And that's where we're going next. Are you with me? Now, please watch this. When I look at this, on an antenna, remember it's rated by maximum value of gain, and if the efficiency is 1, it's just the same thing as the directivity, right? So what is D max? Just take a look. What is the maximum directivity? All right, look here. What's the maximum value of the normalized power? Word is operative word normalized. 1. Are you with me? So the maximum value this can have is 1. That P normalized theta and phi. Like, think of this. Remember how I said this sine squared of theta was the normalized power density? Well, what's the maximum value you can have? 1, right? Just 1. All right. Well, the maximum value, Dmax, right here, would just be when that's 1, so just put this down. Dmax is just equal to 4 pi over the double integral from 0 to pi, from 0 to 2 pi of the normalized power density times the sine of theta d theta d phi. And I'm going to tell you one other thing because I think that you deserve to know this.
You write that somewhere else.
Yeah, I'll put it up here. D max, I thought I could get away with it, but I understand, is 4 pi over, this is a double integral, of the normalized power density times sine of theta d phi. This goes from 0 to pi, 0 to 2 pi. Now really the truth is, if the normalized power density is 0, say we've got an antenna at the Earth's surface, right? Well, nothing radiates into the Earth. Y'all follow me on that? So then the integral would be not from 0 to pi, but 0 to pi over 2. Y'all see that? It's only where the normalized power has a non-zero value. All right? Now, that's the maximum value. I can tell you really the bottom line with gain and directivity. Here's how they really, and I don't, when I teach radar, I do it differently. When you talk about gain particularly, all right, the gain of theta and phi, what it really amounts to is the average power density from with the antenna you're using, divided by what the power density would be from an isotropic radiator. So what would antenna radiation be from an isotropic radiator? It would be P transmitted over 4 pi r squared. You follow me on that, class? Here's the actual power density. Now you would need to do the analysis to figure out how much total power is transmitted, right? And then you would have to find out what the power density was as a function of angle from the antenna to get this average power, right? But once you have that, then you just divide it by the transmitted power over 4 pi r squared, and that is the gain. And it should make sense. It's how much better it is than an isotropic radiator. That's all you're saying with gain. Now, what Dr. Whitmer's book does, he says, all right, mathematically that's gain, and I'll tell you what efficiency is in a second. And what is this directivity? Well, mathematically it can be found using this. And you can get this formula right here. I'm not going to do it here, but you can derive that just based on this. Pick an antenna and I can do it for you, but that's easier to use right there. Okay, so and this is really a figure of merit of how good an antenna is at focusing energy. Take it at that. And in electrical engineering and any engineering, matter of fact, just about any hard science, what you try to do is give a figure of merit that's basically how well something's behaving or really doing what you want to do. You always do this in engineering, and you do it surely in a lot of other places, because you want to have an idea, just right off the shelf product, how good it is. Well, if you've got a gain of 100 dB, it's an amazing product. You don't have those very often, and they're giant arrays, but a gain of 20 dB is reasonable, right? Anything above about 30 dB, now you're pushing the limits, now you're talking about some complicated things, usually, and this is a gross generalization, but it's still true. All right, more on this. Now we're going to talk about radiation efficiency. I hope I can have time today to get into actual thin wire antenna, so you can see how we go right from first principles with a thin wire antenna and get all this. I don't know if I will, but I'll try. Has anybody been viewing these lectures at all?
Yes.
All right, is it okay? I work great. I haven't actually looked at these in a while. The reason I'm asking is the glare thing right here. I know that in the other, for the other classes, they have the camera at the wrong angle because the light's reflection. Not the one you're doing, but this is a summer class that the glare would really kind of blind. But everything's fine in this one? Okay, great. So now we're going to talk about, the next thing is going to be directivity. I'll go through some examples too later. It's now going to be the efficiency, and this is antenna efficiency. And this is the symbol I use for it, EF. It's small epsilon f, it's antenna efficiency. Remember, gain is equal to EF times directivity. Now, directivity has to do with the actual antenna's radiation characteristics only. Has nothing to do with any losses, the directivity here. Gain incorporates the losses. It's the true measure of how well an antenna is performing. So how do you talk about antenna efficiency? Huh? Here's the way I'm going to do it. In antenna, let's do the simplest possible antenna, thin wire antenna, right? Well, right here, when I'm driving that antenna, what am I really seeing here? I'm seeing this. I'm seeing something where I have a resistance. This is wire, but this is going to be a dissipation resistance. It means this is resistance due to the ohmic heating of the actual material. If you have copper and you put current through it, it doesn't have much resistance, but it has some resistance. And the higher the frequency, the more resistance it has, right? Because it's got skin effects. So this is always a loss term right here. Now the next thing an antenna has is, what do antennas do? They take electrical current and they create photons that are launched forever, right? It's really a transducer. It takes current and it creates photons. If that really, you have to have charge acceleration and you have to have time varying current in order to get radiation. Any kind of radiation. So the power that's radiated is associated with what's called the radiation resistance. Write this down. You're going to have now R rad. We're going to show you how to calculate that in a second. Well, either today or tomorrow. This has to do with the power radiated. But with an antenna, it's not always going to act the way you want it to. A lot of times it has an antenna impedance, either a plus or minus J, and you can just call this Z, or call it X antenna. It could be a minus J, which would be a capacitor, but there's something, and this is not wanted. You don't want dissipation, you don't want that JX. Now this JX, say if it was J70 ohms here, that's easy to get rid of. Just put in series with this, and a capacitor that has minus J70, right? Then the total would cancel. You follow me? But you can't get rid of this. That's there. You got to live with it, and that's something you don't want. Now, I'm going to ask you this too. Based on what I just said, you all see how the more current you put through there, the more loss here, and the hotter the thing gets. You all see that? Because of the dissipation. That's why when you get small antennas, you got to be careful. Now, you may not have to do this for a while, but it may come up if you're trying to build a radar. They have a maximum power that you can actually drive them at. It's an average power. If you go beyond that, things start melting. And, you know, like you wouldn't think they would use solder to connect things in antennas. Well, they do, because solder melts to very low temperature. All right, you start driving an antenna beyond its range, and all of a sudden, things come undone, and now you got nothing. And usually they're sealed, hermetically sealed, or they're potted, so you can't get at that thing without tearing the antenna apart. Just remember what I'm telling you. You don't want to do what has been done. So that's what an antenna looks like. Now, that radiation resistance has to do with the power transmitted. Write this down. The transmitted power is actually equal to 1/2 times the I in the antenna squared times the radiation resistance. That's how you get, that's what radiation resistance comes from. So if you have an I there, and again, that's going to be I peak, not IRMS. If you take 1/2 I squared times R rad, you get the power transmitted in watts. Are with me on that so far? So, I didn't, last time I taught this class, I didn't spend this much time doing some of this developmental work, but I think it's necessary because I saw when I took people from my class that I taught, I took them in the radar, they didn't see a lot of this clearly. So that's the reason I'm spending a little more time right here at the basics. Okay, now the next thing we're talking about is an example of this. So here's what I'm going to say. I'm going to say I've got an antenna. Here's a real example. And I've got a G max, right, maximum gain of 20 dB again. So that's 20 dB. And the antenna has an equivalent drive of this. It's got an equivalent impedance. It's got just a radiation resistance, R rad, of 75, and it has a J 75 ohms as well of reactance, right? And I'm going to drive this thing, now work with me here, I'm going to drive this with plus to minus 100 volts, and it will be at a frequency of 3 times 10 to the 8th hertz. Okay?
What's the value of resistor?
Huh?
What is that value?
It's the radiation resistance, R rad,
Or rad, that's equal to
75 ohms. I make them both the same, just to make my life easy.
Okay.
Now I want to know, when I go, here's the actual antenna. I've got a 100 volt source. Now when I go at R equals 10,000 meters, I want to know the average power density, and I want to know what the electric field is, the magnitude of the electric field out here. Now this is a reasonable problem. Can everybody follow me on what I'm asking, why I'm asking? All right, when you buy an antenna, usually they're going to have this information. Not all, but most. At least they're going to say the input impedance of this J75. They might not give you that because they're going to assume you can tune it out, but we didn't tune it out, we're stupid, right? We left it in. So now I want what that power is. Now take a look. So what is I going to be? And this is going to be I peak. Guys, it's as easy as it looks. That's supposed to be 100. It would be 100 over 75 plus J75. Do you all agree with me? So what is that going to be?
100 over root 2.
4 over 3 plus J3. I'm sorry, what did you say?
I was going to say 100 over root 2 times 75.
And you got a phase angle there, but that gets thrown out. That's what you get. What do you get for this exactly? So we got 100, right? So 100 is 4 times 25 over 3 times 25 plus J 3 times 25. So that means I have 4 over really, in magnitude, if I just do magnitude, 4 times 3 times square root of 2. You agree? And we could even do this. We could take this, right? And we could mess around with it. I'm going to leave it like that. That's going to be I, and that's in amps. So after that, what's the transmitted power? Let me put it right here. Well, that would be 1/2, right? Times the radiation resistance, 75, right? Times this squared. So then I have times 16. Oh, because I got to square this. 16 over 9 times 2. And can you give me that? That's really what? 8 over 9, 4 over 9 times 75. Just tell me what that is in watts per meter squared. Anyone?
33.
33? Is that right?
It's
Or
3
no.
over 9. Oh, sorry.
16 over 9 times
Messed
2.
up, never mind.
This is watts. I'm sorry, not watts per meter squared.
Alright.
Go ahead.
1/3 times 100.
It's 33.333333.
Watts of power. All right. Now we've got that. Next, we take a look, and we want the maximum, by the way. I'm at a range of 10,000 meters, right? So now I come over here and I say, well, first I make it look like an isotropic radiator. So I take this, 33.333, and I divide it by 4 pi r squared, that's 10 to the 4th, squaring it, right? And then I have to multiply it by the gain. 20 dB is how many in linear, class? 100 times 100. So it's this, 33.333, and I got 100 up there, and that's just gain times isotropic radiated power density. Are you with me? How many see this? In the far back, I worry about you guys. Can you all see it back there? Can you see it? All right. Yes.
Why is it 100?
Well, the gain of 20 dB is really what? I put that up here somewhere. I guess I erased it.
Yeah.
Gain in dB. If you don't know this, write this down. This dB power is always going to be 10 times log. Gain is a power-related term. It's 10 times the log, and that's a base 10 log of the linear gain. You know, you've had this, with power, it's 10 log, base 10 of a number, right? When you talk about dB power. If you talk about dB voltage, I think you've had this, maybe you haven't. dB voltage is 20 times the log of a linear term. dB current is 20 times the log of that. We'll talk more about that later, but you need to be familiar with this terminology, dB. Okay, so what does this come out to? The average power density, somebody? That's 10 to the 8th, so it's 10 to the minus 6th. 10 to the minus 5th, is that it? About 10 to the minus 5th something?
Is that 33.3?
33, just put 33 in.
Okay. Sure. 4 pi.
Say it again?
6.5 nanowatts.
Nano?
I got
Is that nano for real?
2.6 milli.
Say it again.
I got 2.6 micro.
2.6 times 10 to the minus 6 watts per meter squared. That's reasonable. Is that what you got?
I got nano, or 26 nano.
I got micro.
Well, look, that's 10 to the 8th, right? 10 to the 4th squared is 10 to the 8th. 10 to the 8th, upstairs 10 to the minus 8th, times 10 squared is going to be 10 to the minus 2, right? I got 10 to the minus 2 times whatever's in front of there. It looks like it's micro.
It's gonna be micro.
All right, that's what it looks like to me. All right, class, are you with me? Now that's just for the power density. How do I get the E field? Again, one more time. E field? Yeah. He said just use the equation 1/2 eta naught, or 1/2 E squared divided by eta naught is equal to the power density. So the E field is equal to the square root of 2 eta naught, right, times the average power density, PF. And what is that E field going to be? I don't know. Anyone?
I got it.
You got this one?
Oh, yeah, some arbitrary constant.
Huh?
Some arbitrary constant. I mean,
I'm
math-
boring you, I know. I'm doing my best.
The math works out either way, I assume, right?
44.7 mil.
44.7 millivolts per meter. All right, that's an example, concrete one. Let me just do one more for you. I seem to get behind here. I'll tell you where we're going. Just listen to me. I didn't get there, but we're going to now take an actual thin wire antenna. And we're going to assume a current distribution on that antenna, and then we're going to derive from that current distribution the magnetic field first and the electric field. I'll have to do this next time because it's a little hairy. I can't just give you readings on it. I'm gonna do this.
We'll have a quiz on Friday.
Hey, did we vote on the exam?
No.
Oh, who was supposed to remind me?
I was trying to, but you kept going.
That's not acceptable excuse. All right, next time, everybody do this. As soon as you get in here, remind me to vote on the test. You're going to vote on it, all right? You're going to pick the dates. I'll say it again, but Monday test on average you score higher than any other day of the week. Friday's usually the worst day of the week.
You say Monday, do you mean next Monday
No,
or
no.
Monday after?
It means, you can choose it if you want the next Monday, but anytime you want to test, it's fine.